Now, for those of you that aren't acquainted with me, my name is Chris Morisette, and I'm the Novice Chairman for the Houston Astronomical Society. I want to welcome you to tonight's program, which I think you'll enjoy. I'm going to share my screen right now, so hopefully you can see my presentation with the title October Novice Meeting. Thomas, can I get a confirmation on that?
I've got it. Looks
All right.
clear.
All right, perfect. All right, great. So listen, welcome everybody to tonight's meeting. I think we got a really great meeting for you tonight. This time of year is really cool in terms of going out and observing the night skies. So a lot of cool objects that we're going to be looking at tonight. And as a result, we'll be talking, the main focus of our meeting tonight will be navigating the autumn sky. So with these quarterly topics, what I like to do is go through a refresher around navigating the night sky, talk about signposts, and then get into a discussion on the various objects that we're going to be able to see out there this fall. I've got a short presentation called Astronomy and the Nobel Prize to kind of supplement the end of the program. And then I've got a short one slide bulletin for novice presentations that are coming up in 2025. I'm in the process of developing that and want to get people's input. So that's what we have planned for tonight. If you have questions, as always, please go ahead and write those in the chat. And then when I finish up on the presentation, I'll go back to the chat and we'll go through the questions in the order that they came in. All right. Well, just kind of before we get into all the details here, I did have a chance to go out to the dark site this last weekend. I think there was a Saturday night trip that was organized by Joe Califf, and I hope people had an opportunity to take advantage of that. I went out Sunday night and it was glorious. Conditions were never better, and all my equipment worked the way it was supposed to. So it was a wonderful evening out, and it really kind of drives home the value of being in HAS and being able to utilize that dark site because it's a wonderful asset. Okay, so navigating the night sky, let's go through a quick refresher. As you all may know by this, if you've seen my presentations before, I am a big proponent of the skymap.com website. That's skymaps.com website. They have a free monthly map that you can download and use to go out and use that as a learning tool to understand what the various constellations are in the night sky month by month. So this is what we have for October 2024, and we're looking using this map in its current configuration. We would be looking south, and what we would be seeing as we're looking up into the night sky, in particular, I just want to point out Pegasus and the Great Pegasus Square and Andromeda. Those are two pretty prominent constellations that you'll see in the night sky and that we'll be talking about. You'll also be able to see the summer triangle up here, which is going to be one of our signposts for this time of year. And that's what we're looking at when we're facing south. We turn the map upside down, then we will be, and we turn around and face north. This is what our view of the night sky would look like. And in particular, I want to draw your attention to this small constellation called Cassiopeia. And Cassiopeia will be, again, another, not an official signpost, but it'll be a marker for us to use when we navigate around to find various objects out in the night sky. So skymaps.com, I highly recommend it. It's free and a great tool. Again, when we talk about the positions of various stars, nebulas, galaxies, we can find those by utilizing two coordinates, one called right ascension, which is similar in respects to longitude on a terrestrial map, and declination, which is analogous to latitude on a celestial or on a terrestrial map. So those two coordinates will define the location of any deep sky object that we might want to go locate out in the night sky, or on a map, if you will, of the night sky, like the Deep Map 600, which I've referred to in past presentations. So right ascension, declination are two really important parameters. You'll also notice here that we have this thing called the ecliptic. And the ecliptic is the plane in which the sun and the planets reside, and it's at about a 23-degree tilt to the North and South Pole, or the North Pole rather, on Earth. And this is where we're going to find the planets, we're going to find the sun, and roughly speaking, we'll find the moon here as well, although the moon's orbit with Earth is a little bit off, if you will, from the ecliptic, but it's close enough. So this is the celestial sphere, right ascension, declination, the ecliptic. Key things to remember. Here's another picture that shows those two uh, uh, equators, or that it shows the celestial sphere and then shows the celestial equator, which in the previous picture would be this blue line and the plane that it forms. That would be, this blue line right here is our celestial equator. The ecliptic plane is the plane that's at the 23-degree tilt, which has the sun and the planets. And then also included here is the galactic equator, which is where the galactic disk of the Milky Way resides. And it's at about 63-degree tilt from the celestial equator. So kind of gives you a different view of things. This next picture really, to me, kind of puts it all into perspective, because here I can see the Milky Way, I can see the sun and the ecliptic, and I can see the Earth, and this really kind of puts it in focus. But what you see here at this point right here, we're at the fall equinox, and this is approximately where Earth is in our orbit, in our annual orbit around the sun. And this is the position that we're at when we go out and look at night into the night sky and look at various objects. We were up here during the summer, back in late June, early July. And at this point, we were looking during the night, we were looking directly into the core of the Milky Way. We've changed positions now, and we're looking out towards deep space away from the galactic plane, similar to what we did in the spring. The exception being we don't have the plethora of galaxies that we see in the spring out here, but we do have two really dynamite galaxies that we're going to talk about tonight that you can see very clearly from our position during the fall. And so this is where we're at, and to kind of put it in terms that we can all understand, this is where we're at in our annual orbit around the sun. Another thing that I like to review is a easy way, a manual way, pardon the pun, to measure distances out in the night sky. So with the width of a pinky finger held at arm's length, you can measure 1 degree of distance in the night sky. 3 fingers will give you 5 degrees. Closed fist will give you 10 degrees. Hook'em horns gives you 15 degrees. And then the Hawaiian sign for hang loose gives you 25 degrees. Again, if you hold this at arm's length, you can use those to get an approximate measure of distances out in the night sky. So again, pardon the pun, but a very handy little tool. So that's just a quick refresher on navigating the night sky. Now we're going to talk about signposts, which I think are really important. Here, remember, if you remember back in the summer and the spring, we were able to really utilize the Big Dipper in Ursa Major to navigate around the sky and find various objects. Right during autumn, it's the Big Dipper is going to be of limited value because at prime time in the in the evening in the fall, you're going to see the Big Dipper hugging the horizon, and as a result, you're really not going to be able to utilize it as a signpost because, arcing to Arcturus would put you down below the horizon. And if you've got a lot of trees or a tree line, you wouldn't be able to see it. Now, when I was out Sunday night at the dark site, and it wasn't totally dark, but it was getting close. I was able to utilize Arcturus as a star to star align my astrophotography system. So it was up high. The Big Dipper was up high enough to utilize it, but shortly thereafter, it was down below the trees and you couldn't use it at all. And Arcturus was below the horizon. So, and then that's similar. The similar story for the winter. Uh, the Big Dipper is just not going to be in a position to help us out much. Here is here is a picture of our night sky with all the gory details, and I have highlighted here in green. These green boxes represent the section of the night sky that we're going to be looking at. And so over here, you'll notice that we still have the ability, and there still is value in using the summer triangle. It's up, it's visible, and it can help us move around the night sky. The Teapot as well is still a useful asterism to navigate around the night sky. Before Sunday night, and when I was putting the presentation together, I was kind of looking at that and saying, I wonder how true that is, because I can't see the Teapot here from my house. So when I was out at the dark site, yes, indeed, the Teapot was present and available for use, probably up until about, I'd say 1:30 in the morning. Its position was such that the spout was down and it was actually pouring tea, but we could utilize it for navigating, and it was useful as a signpost even in the fall. As we get into November and December, it's going to be less and less valuable. We'll have a shorter period of time to take advantage of it, but certainly during October, it's a useful signpost for us to take advantage of. Over here, so really, if you think about this map, as we progress, we're kind of going right to left. And so this is kind of where we would be at kind of early in the fall. And then over here is kind of where this section comes into prime time. And then we'll roll into Orion in the winter sky, going again right to left. Over here, the one item that again I want to point out, and again I haven't christened it as an official signpost, probably need to do that, but there's a constellation called Cassiopeia. Cassiopeia is a very well, at least as far as the visible stars are concerned, that I can see here in the suburbs of Houston, it's probably about 5 or 6 stars that form an M as it's going up the horizon towards the meridian, and then when it gets over on the other side, it'll look like a W. The reason Cassiopeia can be used as a signpost, though, is because Cassiopeia is very easy to spot. Just like Orion is, just like the Summer Triangle is, Cassiopeia is a very visible and a very apparent, very recognizable constellation. And as a result, probably deserves to be classified as a signpost. And again, we'll be utilizing Cassiopeia tonight as well. Okay, so that's a little bit on navigating the night sky, talking about some of our signposts. And now what we'll do is we'll dig into the autumn sky objects, which are among my favorites of the year. All right, so just bear with me a second. Just take a sip of water. Thank you. Here we're going to start out with the summer triangle. So if you remember, the summer triangle is composed of three really bright stars, Deneb over here in Cygnus, Vega, which is in Lyra, and Altair, which is down in Aquila. These three stars form the summer triangle, and for this part of the year, we're going to focus our attention really around Deneb and the constellation of Cygnus. And so we won't have to be moving around too much to get some really cool objects. So we're going to talk about the Veil Nebula, the North American Nebula, and the Crescent Nebula. So let's start out with the Veil Nebula. And the Veil Nebula is about, let's go back up here real quick. Excuse me. The Veil Nebula is down here. So if you are looking at Deneb, you can make out these other stars that kind of make the wings. You want to come down and then over to one of the side stars that form the wing of Cygnus the Swan. And that's where we're going to find the Veil Nebula. And it's about 12 degrees below Deneb. So you hold up three fingers, that's 10 degrees. That's going to give you an approximate distance from Deneb. But really, if you focus on this star down here, you should be in good shape. But this is the Veil Nebula. The Veil Nebula is about 2,600 light years away from Earth, and it is in the constellation of Cygnus. This item that you're seeing here is a supernova remnant. So, in effect, what you're kind of looking at is the effect of a large blast and what that shock wave looks like emanating out from the star that exploded long time ago after it ran out of fuel. So a few things I wanted to highlight about the Cygnus loop is that there are a couple of prominent asterisms that are in this, or not asterisms, but nebula, separate nebula that are in the loop. This right up here is the Western Veil Nebula, sometimes referred to as the Witch's Broom. And then down here is the Eastern Veil Nebula at the bottom on the kind of the other side of that blast wave, if you will. The Western Veil Nebula is about 53 light years in length. The Eastern Veil is about 100. So they're pretty prominent nebulas here. It's believed that the star that created the Cygnus loop, this explosion, was about 20 times larger than our own sun. So it was a large star, and when it came to it the end of its life, the result was a supernova. The reason that you see these beautiful colors here is because that shock wave has so much energy in it. Um, it's actually energizing and making the ether around 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 the Cygnus loop glow. And so that's why you're seeing all these beautiful colors. That shock wave is exciting this interstellar medium, and that's what's making it glow. You know, like in an emission nebula, you have radiation off of the stars that's making that happen. Here you have the energy from that shock wave. So it's just a really spectacular item. This is a really wide field of view object here as well. So if you're going to go out and look at it, you know, you want to make sure that you have a telescope that'll give you a decent field of view. I have here a picture of the Eastern Veil Nebula, and this kind of shows you close up what that that bottom one looks like here. Down here, it's kind of oriented 180 degrees from what we saw in the previous slide. But you can kind of make out this twisty, turny, almost looks like lightning kind of effect here in the ether. And again, that's the result of the shock wave from that supernova many years, thousands of years ago. So that's the Cygnus loop. We're next going to go on to the Crescent Nebula. And forgive me, I'm going to just hop back up here. So the Crescent Nebula is right near that center star. So we go to Deneb and then we follow the stars down to the wings of Cygnus, and it's this star right here. I guess it's kind of like the breastplate of Cygnus, the Swan. That's where we're going to find the Crescent Nebula. Now, the Crescent Nebula is a bit of an odd bird. Um, this item, just kind of give you some basics, it's about 5,400 light years from Earth. So it's about twice the distance as the Cygnus Loop. And it's relatively small, so it's only about 32 light years in size. Now, this is an emission nebula that was discovered by William Herschel, and it's an odd duck because the Orion Nebula, you have emission, you have the glow of the interstellar medium in the Orion Nebula. It's a result of the energy coming off of the stars that are being born, and they're ionizing the hydrogen in the cloud. That's what's giving us a nice, pretty glow. Here, what's happening is you had this star, it's called a Wolf-Rayet star. It's Wolf-Rayet star 136. And what had happened about 400,000 years ago, when it was becoming a red giant, it had ejected some solar winds off into the surrounding ether around that star. And these winds, because there's really nothing out there to stop the winds, just kept going and going and going, albeit at a relatively slow rate. Later on, the Wolf-Rayet stars are very energetic stars. I don't know all the physics around it, but there are a lot of metals, a lot of ionized nitrogen and carbon, and I don't know this for a fact, but I got to believe that that's one of the reasons why these stars are energetic. So, long story short, this star is ejecting off a lot of material due to these solar winds. And it's this new material that's being ejected that's colliding with that old stellar wind that was created when it became a red giant. And that's what's making this glow appear. I'll be honest with you, this is one of these things that I'm still learning and studying. So um, my explanation is pretty basic, but but it's really unusual. It's not like you'd see with a normal nebula. And if you look at this item here, the shape and the shape of this thing, the texture of it really kind of reminds me of the human brain. So again, a really odd but beautiful object that's located in Cygnus. Okay, so next up on the agenda here is the North American Nebula, and I'm going to take another sip of water. Thank you. And this is a really wide field of view object. The picture that you see here is really, really wide field of view. And the question, can you find the North American Nebula? Well, I think if we look close enough, we're going to see it right in here. You can sort of make out the Gulf of Mexico here and the red H2 regions of the nebula here, and that kind of is your tip off. So that's where that's the North American Nebula. And this nebula is located right at Deneb. So you don't have to look any farther than, one of the corners of the summer triangle, and you're right there. This next picture right here is a close-up. The North American Nebula is very wide field of view, a very large item. It's about 10 full moons in size, so that'd be about 5 degrees. So it's a very large object, but it has a very low surface brightness, so it's difficult to see without a telescope of some sort. I'm not even sure you'd be able to make it out with binoculars, um, but it but it is a very wide field of view, and it's a very beautiful object. Again, this is an emission nebula, and there's an item or a feature of the North American Nebula called the Cygnus Wall, and that's what you see down here, which kind of is, I like to think of it as like the Pacific coast of Mexico and Central America. But this is what's referred to as the Cygnus Wall right here, and that's a very energetic, very active star-forming region in the North American Nebula. Again, this item is about 2,600 light years away from Earth, so it's relatively close. And again, a very beautiful object. So moving on, what we're going to do now is we're going to take advantage of the Teapot, which is one of our signs. So if you are looking at the summer triangle, you can go from Deneb down through Altair to the Teapot. And out at the dark site Sunday, if you've all been out there before, you can make out the Milky Way, or at least you could the night this last weekend, because conditions were just wonderful. And so if you just follow the the Milky Way galactic disk down to the horizon that is going to be on the southwest corner of the dark site, that's where you're going to find the Teapot. And again, the Teapot was there, but it was very low in the sky, and it was in a position where it looks like you were pouring tea. So how do I utilize the Teapot to get to the Helix Nebula? So what you can do is go make a line from the spout of the Teapot here to here, and then from this point go about 40 degrees over to the left towards the handle of the Teapot. And if you do that, you should end up at the Helix Nebula. And so this is the Helix Nebula. This is a planetary nebula. And a few basic facts about the Helix Nebula. It's about 800 light years away from Earth, so it's really close. And it's very small. It's about 3.4 light years in size. So in order to see something like this, you'd probably need something on the neighborhood of like a 10-inch Dobsonian telescope like I've got here to my right in my den. That would certainly be a telescope that would give you adequate light collection and magnification to view this. And you wouldn't see the colors. It would look rather grayish in tone, but you could definitely make it out as a distinct deep sky object. So a planetary nebula, if you may recall from previous presentations, is what you get when you have a star that runs out of fuel and dies, and that star is approximately the size of our own sun. Larger stars will collapse catastrophically and form a supernova. Here, what you get is a planetary nebula. The star will collapse down into what's called a white dwarf. And that white dwarf is still hot. It doesn't have any fuel left, but it's still really hot and emitting a lot of radiation. And that radiation is what's making the resulting gas layers that were left from the star, making those glow. So that's what you're seeing here, is that radiation making the leftover shell of gas around the original star glow. So this is the Helix Nebula. It's one of the larger planetary nebulas, so it's a good target to go after. I have seen the Ring Nebula, which is smaller than this one, with a very large telescope. I think it was Stephen Jones's telescope, and I can't remember if it was an 18 or 20-inch diameter telescope. It was really big, and we could see it, and it was really wonderful to see. But with this smaller telescope, say this 10-inch that I'm referring to here that you can't see, that probably would get you in the ballpark. So that's the Helix Nebula. Okay, so now what we're going to do is we're going to go down and look at a couple of objects that are in Pegasus and Andromeda. And it's at this point we've got to rely on our new signpost, if you will, called Cassiopeia. So if we're facing north and we're looking up into the night sky, kind of on the right-hand side of the sky, we should be able to make out this W looking set of stars. And when we can find that, we are in Cassiopeia. So that is a good place to start, at least if you're looking in the in your neighborhood where there's a fair amount of light pollution. Out at the dark side, it's still a useful place to start and to look. And then you can see very clearly as you go from Shadar, this star here on one of the points of the W down, you're able to go here and you're able to find Andromeda. So the Andromeda constellation are these two legs right here that you see here, out to here, and from here out to here. This actually connects with Pegasus, which is the great Pegasus square, and then some of these tendrils that come off of Pegasus. But Andromeda, when you go again, when you're out at a place like the dark side and you follow this path down from Cassiopeia, you'll be able to make this out very easily. Okay. So the first item that we're going to look at is Stephan's quintet. So in order to get there, what we've got to do is we've got to find Pegasus, the great Pegasus square, and then we got to go up to this top tendril, and then out between two stars called Matar and Peg, and the quartet is about here. Now, here's the quartet, and it is a very small, distant group of galaxies. So in order to see this, you're really going to need a really large telescope, at least a 10-inch, if not greater. But it is a worthy target to go after. And so let's talk a little bit about Stephan's quartet. This is a small group of galaxies called the Hickson group, and they're really, let me point out before I get into that, let me just point out briefly that we're looking at 5 galaxies. So we're looking at 1, 2, 3, 4, and these form that Hickson group, that Hickson 92 group. And then here is another galaxy that is in the foreground. So they're in the same field of view, but they're really in different groups because this one is much closer to us than these 4 galaxies back here. As a matter of fact, these 4 galaxies back here are about 320 million light years away. So they are just way the heck out there. So this is Stephan's quartet, or quintet rather. One thing that I did want to point out is on this galaxy that's in the foreground, NGC 7320, it has some very prominent regions, very prominent H2 regions, which are in describing what they look like red blobs, but they're really star-forming areas. Now, you really can't make it out very clearly on this picture because the object's so small. But if you look closely down here, you can see a red blob in here as well. But that's Stephan's quintet. Again, this is really a challenging object to go look for. Certainly something that I'd need some help finding because it's so small and it's so distant, but very cool looking. Now, don't despair because we have a object that is going to be easy to find, and when you find it, it's just going to be spectacular. So going back to our little map here, we wanted to find the Andromeda Galaxy, which is right here. And we can find that one of 2 ways. You can come down from Shadar down towards the one of the arms of Andromeda and kind of find it that way. The easier way, though, is to find this leg right here from the Great Square and follow it out 1 star, 2 star, and then go up here about 5 degrees or so. Again, when I was out there Sunday night, I could follow those 2 stars out on the leg and go up, and I could almost make it out naked eye. It's that large of an object. It's that bright of an object. I had a pair of binoculars there with me. I was actually photographing Andromeda, so my telescope was taking pictures of it. But while I was sitting there babysitting the equipment, I got my binoculars out, and man, it's a knockout. I mean, easy to find, and with binoculars, it's really a good view because, and I'll go back down to the picture, because you have so much dark sky around that hazy looking galactic disk and that distinctive core that you can really make it out. In a telescope, sometimes it's a little bit difficult but with binoculars, you can't miss. And binoculars at the dark side, you can't miss. I've even seen it here at my house in Kingwood, and it's just a wonderful object to behold. So why? So if you've noticed here, I'm kind of gushing over Andromeda, and it's probably one of my favorite, if not my most favorite, deep sky objects. For a couple of reasons. One, it's beautiful and it's very large, and it's our closest neighbor that is a spiral galaxy, largest spiral galaxy closest to Earth. So it's really dramatic. And then it also holds a really important place in history. I'll tell you a little bit about that, but let's talk about some basic facts here. Andromeda is about 2.5 million light years from Earth. Again, the largest spiral galaxy to Earth. And it's about 130,000 light years from end to end. Our own Milky Way is 100,000, so it's about 30% larger than our own galaxy. So it's a bigger galaxy. Um, Again, it's a beautiful galaxy. Here in this image here, you can see two companion galaxies. This is M32, and this is M110, and these are gravitationally um, uh, bound or attached to Andromeda. It's thought that M32, the smaller one over here, actually passed through the disk and actually warped the disk. But again, it's a beautiful galaxy. Its place in history is really interesting as well. So uh, M31 Andromeda was long thought to be a nebula that was in the Milky Way. Okay, and a large nebula, but a nebula that was in the Milky Way. Edwin Hubble, using Cepheid variables, uh, stars, was able to deduce that no, this is actually another quote unquote island universe, and it's much farther away from us than we had originally anticipated. And so Edwin Hubble determined that this was much farther away. And I think that that discovery just really opened up our eyes and our horizons on how big the universe really actually is. I think up until that point, the universe was thought of as the Milky Way. And once we figured out Andromeda was way the heck out there, it was just kind of a whole new paradigm in terms of how big the universe is. Um, Another interesting feature about M31 is that rather than receding away from us like most objects are, most galaxies are, it's actually coming towards us. So in about 2.5 billion years, um, it's going to collide with the Milky Way and turn into a single galaxy. And if we go back up to Stephan's quintet, you can kind of see that phenomena taking place here. These two galaxies here appear to be merging, and then similar to what we can expect with the Milky Way and Andromeda. Um, don't know if we'll be around that long, but that is that's going to happen one way or another. So that's Andromeda. It's a great target. It's an easy target and well worth your while. If you're new to astronomy, it's really exciting to see that. The last item here in this part of the sky, I'm sorry, let me back up a second. The last galaxy that we're going to look at is one called M33 called Triangulum. So in order to get to Triangulum, what we have to do is go about 10 degrees southwest of M31. So here's M31. We come down here to M33, and again, that's about a 10-degree um, distance between the two. Um, this is another spiral galaxy that is in our local group. And you can see this is very distinct, has these very distinctive arms that are spiraling out from somewhat of an undefined core here in the center. And this galaxy is about half the size of the Milky Way. It's about 51,000 light years in size, and it's farther out than Andromeda. Andromeda was 2.5 million light years away from us. This is about 2.8. So this is a really cool one. I tried like the devil to find this one again out at the dark site with my binoculars, and I wasn't able to find it. Doesn't mean it can't be done. I'm getting up there in age and my eyesight isn't what it used to be. But I would suspect that a telescope, a Dobbs, at 8-inch, 10-inch Dobbs would be something that you would need in order to get to the get to see this object. And it's just, excuse me a second. So a couple of features here that are kind of cool to look at. There is actually a area of H2 ionized hydrogen down here in the southwest corner, right here. This is actually a separate object called NGC 604. It's a very large area. It's about 1,500 light years in size, just the quote unquote region nebula, if you will, that's in M33. But it is distinct and you can see it from Earth. So I think that's kind of amazing. You know, we're used to looking at deep sky objects like nebula and things like that in our own Milky Way. This one's one that you can actually see in a very distant galaxy. So that's M33. And then the last one on our hit parade here is going to be the Heart Nebula in Cassiopeia. So here you can see Cassiopeia sitting upside down in her throne. Has kind of the M shape to it. And if we look here, we can see what Cassiopeia, or where the Heart Nebula would be in relation to Cassiopeia. So here's the kind of the bulk of Cassiopeia. You're missing. There's a star up here that's not pictured. But if we follow this down, we can find the Heart Nebula, and it's about it's slightly right to the to this point right here on the tip of Cassiopeia. So that's the Heart Nebula. It's about 6,200 light years from Earth. So again, relatively close, and it's a rather large nebula. It's about 107,000 light years in size. There's a small group of stars here in the center that are responsible for ionizing and making this these clouds of gas and dust glow. And that's what you see right here. And in addition, the stellar winds from these very hot active stars have actually worked to push out material from here and here. So it's actually created a couple of voids in the nebula. So again, kind of, you know, going back to that Wolf-Rayet star in the Crescent Nebula, you've got these winds that are actually significant enough to push material out. Very cool looking object, very difficult to see. Again, something that you probably wouldn't be able to make out with binoculars because its brightness is very dim, but it is rather wide field of view item. So with that, that really kind of wraps up the deep sky objects that are available to us during the fall. Here's my handy dandy chart that shows each of the objects that we looked at, and also my suggestions on what kind of equipment or aids you would need in order to find these. Again, Andromeda, depending on where you're at, you can see naked eye, but binoculars for sure will get you a beautiful view of Andromeda. The rest of these are you're really gonna have to rely on a telescope because the surface brightness of the objects are not as they're not as bright as Andromeda, so it'd be tougher to see. So that's my handy dandy chart. I saw this chart came out. I don't know if y'all saw this as well. This came from, I think, Steve Goldberg, but I love this chart. It's sort of like a periodic table for viewing. It conveys a lot of the same information that I was trying to do with that previous table. It's for Messier objects only, so M31 and M33 show up here, but this gives you an idea of which objects are, you know, the difficulty of objects in terms of being able to view these, what these objects are, when, you know, what time of the year you can see these objects. A really cool chart. And again, if you are interested in getting this, again, I think Steve Goldberg sent this out, but if you missed that email, you can certainly send me an email and I'd be more than happy to send it to you. But I think this is really, really a wonderful tool. To wrap up here, just some upcoming celestial events. I think the one that's big on everybody's radar screen is this comet that's out there, Comet 2023 A3. It's currently in a constellation of Leo, and here are the right ascension and declination coordinates for that comet. Um, it has been visible in the early morning. As a matter of fact, on Monday morning, I tried to see if I could find it, but I didn't have any luck. But it was visible in the early morning. According to what I could glean from my internet searches, this comet is going to disappear tomorrow. And during the second half of October, the comet is actually going to be visible to us in the west after sunset. So rather than having to get up really early in the morning before sunrise, uh, hopefully we can see this thing in the west after sunset. I also tried to determine when this thing will be off the radar screen and not visible for us. And the best I could come up with was the drop in brightness at the end of October. I suspect probably by November, by Thanksgiving, this will be an item that we won't be able to see anymore. But very cool. I've seen a lot of pictures sent out by various folks capturing the comet, and it's really a beautiful object. As far as the moon, planet, and stars are concerned, not a whole heck of a lot going on. We got Mars going into conjunction around November 18th. And if you remember from last month's talk, conjunction means that Mars is at its farthest point from Earth on the other side of the sun. And then Jupiter will be in opposition December 7th, which means it'll be at its closest position and will be in kind of prime viewing, uh, uh, in a prime viewing position in the sky. We got a few meteor showers that are happening here. The Orinids, Aretides, Delta Ar Argides, which I'm probably not saying correctly, and Eta Cetids. These are some meteor showers that are happening. The Orinids are a major meteor shower, so probably one to put on your list. If you ever wonder where I get this information, there's a newsletter that's sent out by the Astronomical League called What's Up, Doc? I think you probably all should be getting a copy of that because we are members of the Astronomical League, and it's got all this information in there. And again, if you haven't seen that or want to get a copy, I'd be more than happy to send that to you if you just shoot me an email. And I'll show you my email address here in a bit. Okay, so that is the main crux of the presentation tonight. I encourage you to get out there and stargaze. The weather's finally getting cool. It's nice to be outside, and there are just some really cool things to see. Okay, so kind of a little pivot in topics here. I wanted to talk just a little bit about astronomy and the Nobel Prize. Had the opportunity to go to the Nobel Prize Museum in Stockholm, Sweden this summer, and it was a wonderful, a very accessible museum. And the one thing that struck me was how much astronomy and astrophysics was recognized by the Nobel Prize. So that was cool. And I said, I've got a presentation I can bring back home from my trip. So that's a picture of the Nobel Prize. It's kind of an inlay in the floor. And I took a picture of that, really kind of cool looking. So I'll just hit briefly a little bit of the background and general information on the Nobel Prize. I'll then go through some key Nobel Prizes here in astronomy and astrophysics. Uh, talk about the general relativity, which is kind of a unique story, a surprising story between about in relation to the Nobel Prize, and then I'll end with a short video that I saw at the museum called Cosmos. Okay, so here's a little bit of background. Alfred Nobel was a Swedish industrialist during the 19th century. He's best remembered for his work that he did with dynamite. He was able to make stable forms of the explosive, and as a result, was able to, people were able to utilize that for mining, railroads, all kinds of excavations. It was, the kind of the height of the Industrial Revolution, and dynamite really played a key role. When he came to near the end of his life, he stipulated that his estate would fund a prize, and that prize today is currently awarded at about $1 million per prize. And what Nobel wanted to do is he wanted to make sure that experts were determining who the prize recipients were. So he didn't want it to be a popularity contest. He really wanted experts to weigh in and determine who should get the prize. There are several prizes that are awarded, and here's the list of prizes. This is a picture right here of a keychain that I bought at the gift shop there at the museum. So here is physics. This is chemistry, or prizes awarding chemistry. There's a prize awarded for medicine and physiology, literature, peace, and economics. Couple of things about, so the original 5 were the physics, chemistry, medicine, literature, and peace. The economics prize came later. That was sponsored by and funded by the Bank of Sweden, but administration of the prize is done by the Nobel Foundation. The Peace Prize actually is determined by a committee of 5 people that are appointed by the Parliament of Norway, which is kind of odd. Now, at the time he died, there was a union between Sweden and Norway, so they did have close relations, but even before he died, that was beginning to kind of unravel. So that was kind of this prize was viewed in a couple of different ways. A lot of people thought, hey, this is a very magnanimous way to spend your estate. Others were a little bit more dubious. There was a lot of nationalism in Sweden, and the fact that they were having this international prize was kind of flaky. And then added to that, the fact that one of the prizes was going to be administered by this country that was beginning to kind of break away from Sweden. So a little bit of skepticism, but I think over the years it's proven to be a value to society. So certainly cool. These prizes were determined primarily by Nobel's personal interests. Chemistry obviously was big because that's how he made his living. Physics was obviously closely linked to chemistry. Medicine and physiology, they say that he was somewhat of a hypochondriac. So he had kind of a interest in medicine and physiology because he was always going in and getting ailments checked out. When he was young, he was into literature, so that kind of stuck with him with the rest of his life. And then the Peace Prize kind of came about, at least, from what I read in the displays at the museum, because while dynamite was used for commercial purposes, it also had a military purpose. And he began to say, hey, gee, I made a lot of money off of killing people using dynamite through for military purposes. Maybe we need to give back a little bit. So there are 2 museums. There's one in Stockholm, which you see pictured here on the right. That's the Nobel Museum. And then here's the Peace Center down in Oslo. Little bit of a funny story. I was in Oslo for only a day, and I walked by the Peace Center, and I thought, well, do I have time to go in there and look? And I said, nah, don't worry about it. When you get to Stockholm, you'll have more time, and you can get all the information you want on the Peace Prize. So I got to Stockholm and quickly realized that all the information on the Peace Prize was in Oslo, Norway. So I missed the boat there. But hey, what the heck? So let's, how does this deal with astronomy? Here are some facts about the relationship of astronomy and astrophysics to the Nobel Prize. So approximately 20 to 25 Nobel Prizes have been awarded for work directly related to astronomy and astrophysics. And the prize that's awarded for the work in astronomy and astrophysics is the Physics Prize. There's no dedicated, as you can see from the previous slides, there's no dedicated astronomy or astrophysics prize. Excuse me. So the physics prize is what people get. So they hedge their bets a little bit, 20 to 25, because I think some of the particle physics work that has been awarded Nobel Prizes, while not directly related to astronomy, did have an impact on astronomy. So that might be why it's 20 to 25. But what I wanted to do is just share with you kind of the a recent set of 10 that definitely were astronomy related. So in 1967, Hans Bethe got a Nobel Prize for his work on stellar nucleosynthesis. In other words, explaining how stars produce energy by fusing their elements. 70 for Anthony Hewish, won for the discovery of pulsars. 1978, Arno Penzias and Robert Wilson won for their discovery of the cosmic microwave background. This was the two, I think this was the two uh, Bell Lab guys that were building this telescope in New Jersey and were wondering where this nuisance noise was coming from. And lo and behold, it was the cosmic microwave background. Chandrasekhar won for his work in defining the Chandrasekhar limit. So if you've got a star that's 1.4 times the size of our own sun or larger, you're going to, when it ends its life, it's going to either result in a neutron star or a black hole. Anything smaller ends up as a white dwarf. In 2002, Riccardo Giacconi won for his work in X-ray astronomy that led to the discovery of X-ray sources like black holes. 2006, John Mather and George Smoot won for their work on the Copia satellite, where they mapped out the cosmic microwave background. What they did that kind of took the previous uh, uh, prize winners' work, kind of built on it. They actually went out and mapped um, uh, small temperature variations in the cosmic microwave background, and then were able to deduce from that that those differences would lead to or could lead to the formation of galaxies and other large-scale structures. To continue on here, we've got 2011 Perlmutter, Schmidt, and Reese for their discovery of the expansion of the universe and that it is accelerating. And that also led to the theory of dark energy. You had in 2017, Weiss, Barish, and Kip Thorne for their work at LIGO in discovering gravitational waves. James People for his discovery of along with a couple others of the first exoplanet. And then in 2020, you had a trio of people, Penrose, Genzel, and Gez for their work on black holes. So just kind of a sampling of award recipients, but very impressive. The museum asks each Nobel Prize recipient to donate an artifact for display. So what you'll get kind of some wigged out stuff from the literature people that are awardees that win the literature prize. They'll give their pipe or their slippers or their um, um, bathrobe that they used when they were writing their novel. In this particular case, George Smoot, who was involved in the Copia satellite, donated this prototype antenna, which was used to measure the cosmic background radiation or those temperature variations. So that's an artifact that was given. And here is another artifact that was donated by Kip Thorne. He was the person associated with LIGO. And essentially, it's a plate that kind of looks like a saw, but it's actually a screen to keep out intrusive light during gravitational observations. And the teeth are cut in a very intentional way to kind of provide a statistical distribution so that you get a more effective screen. So I thought that was really cool. So those are the recipients and some of the artifacts that were given out. Now, let's talk about the general relativity story. Einstein was not awarded a Nobel Prize for general relativity, which is shocking because that's probably one of the most profound discoveries in human history. Um, some of the displays at the museum stated, well, at the time it was still kind of out there as far as, you know, could we believe it? Is it for real? There had in fact been uh, evidence to support the gravitational lensing when an eclipse was witnessed down in Africa right after World War I. So that part of the theory was proven out, but the rest of it was still up for grabs. Um, Instead, Einstein was awarded a Nobel Prize for his work for the photoelectric effect, and it was probably not one of his most important discoveries. Um, this was considered one of two great blunders. Einstein not getting a Nobel Prize for general relativity, and for Mahatma Gandhi not receiving the Nobel Peace Prize. I mean, Gandhi is synonymous with peace. The fact that he didn't get a Peace Prize was surprising to me. So just a quick aside there that I thought was really interesting. And then I'm going to leave you with this. I'm going to kill the sound on this. This is a display, a video that I saw in the museum. And for me, it kind of reminds me of the expansion of the universe. And as you get farther and farther away from this, you can see the larger structure of the universe. You can see filaments forming, voids, uh, walls. It's just, cool. I stared at this thing forever. So I took a video of it and I thought, what the heck, I'll throw it into the presentation because I just get a kick out of it. And so that's it. So that was my visit to the Nobel Prize Museum. If you ever get a chance to go. It's just wonderful. Um, so let's wrap things up. Novice presentations for 2025 are coming up upon us. I'm putting together a presentation schedule between now and the end of the year for next year. I would like to hear from you. If you've got any topic ideas, please share those with me. I'd love to put them on my list and make sure that I'm addressing what the novice, um, folks that are novices in the group would like to hear about. Additionally, if you're interested in making a novice presentation, please consider it. Just kind of relate a story that I had over the back in February. I had an opening in May, and I was talking to Matt Borlange, and he and his wife were really excited. They were getting into spectroscopy, as novices. And I said, hey, that would be a great presentation to make to the group. And Matt was kind of like, well, we're just getting started. We're not really quite sure what we're doing, and it might not be professional or something to that effect. And I said, hey, whatever you guys are doing, wherever you're at in your journey, I think sharing your journey and what you've learned and what you need to, what you have in front of you to learn would be an interesting talk. So he agreed to make it in May, and he did a wonderful job. And I shared that story with you just to kind of drive home the point that, I'm not looking for you to be an expert, but I am looking for somebody that has a story or an experience to share that they think would be of value to other novices. So just want to leave you with that. If if you have topic ideas or you want to throw your hat in the ring for a presentation, please let me know. Here are three email addresses that you can reach me at. The cmorisette@yahoo.com is your best bet, but you can reach me at the other two as well. And I would really love to hear from you. And I'm going to wrap up here now with one last slide. And I wanted to make you aware of tomorrow night's topic called My Astronomy Journey that's going to be presented by Mr. Tim Russ. That'll kick off at 7 o'clock on Zoom. And I hope you all can make it. And with that, I'm done. I'm going to, how do I do? I'm going to stop sharing and see what we've got in the chat room. Okay, so the first one is by Joyce, and she asked, Chris, when you say you were using binoculars, what were you using? 10 by 50. That is correct, Joyce. I was using 10 by 50s. Yes. I apologize for not making that clear, but yeah, those are plenty. I have another pair that I think are 7 by 30. They're smaller, but still, I would in past trips out there, I've been able to find the galaxy with that as well. And then Joyce, you had a comment. Oh, you put in the Messier table. Excellent, great. So if you are looking for that, you can probably grab it off the chat. So thank you for doing that. And then Joyce, you had another question. What's up, Doc, for October? Which I don't think we're emailed. I don't have it in my inbox from HAS. Okay, so and then I see a copy of What's Up, Doc. Joyce, can you come off of mute and
Yeah, so
tell me?
I didn't get it from HAS, but I did get it from Erin. And
Oh,
so there it is for this month.
excellent.
Um, yeah.
Okay, good. Yeah, so that brings up a good point. I'm in the North Houston Astronomy Club and Fort Bend Astronomy Club. I've been getting it from the North Houston Astronomy Club, but it's an astronomical league document, so we should be. I've seen Joe Califf actually send this out in the past, so I think it's kosher for us to share it with everybody. Again, I would just if you've got if you don't have it, you can certainly get it off the chat, or like I said, you can email me and I'd be happy to send it to you. I don't want to send out a mass mailing if I can avoid that though. And then Joyce, you had one last comment. Could you review how the baffle worked? Oh, if only I knew. Let me share that again. Let me do that. Yeah, let me page up here. Well, oh, here. There we go. Oops. Yeah, how does that work? So I'll be honest with you, Joyce, mechanically and where that fits in the LIGO detector, I have no idea. I've gotta believe though that it's a plate that fits in and around where the lasers go in and out, and those lasers probably shine down in between a parallel set of these. That would be my guess, but I'd have to do a little research on that.
It's just amazing how like the simplest things can make such a big difference. And it was just like like that looks like something I could make,
I know.
like so like so what does this do? So yeah, it's just yeah, it was amazing to see
Very
that.
cool. Yeah, it's just a simple plate that looks like a saw that you use if you're up in the north woods of Wisconsin. But there it is. So
Exactly.
anyway, so those are the end of the questions that were in the chat. If anybody has a question or comment, feel free to come off of mute and I'll do my best to field the question. Um, and we'll go from there.
Hey, Chris,
Yes.
this is Bill Spizzeri. You did a great job. You make it look so easy. I know how much work there was to put this all together. You make it look very easy. Thank you very much.
Oh, well, you're welcome, Bill. Thank you for the comments. The kind words. I appreciate that. And yeah, one of the reasons that I like to do this, in addition to learning, this helps me learn about astronomy because I consider myself a perpetual um, novice. But it's just the getting up and public speaking is really something that I try to force myself to do. And so, yeah, I appreciate that because I do rehearse. I just get that out there because I want it to flow. I want it to feel right. And I'm glad you recognize that, Bill. Again, appreciate that very much. James Wooten, you
Yes,
were,
it was a little comment about the Nobel Peace Prize not be given to Gandhi. I know that there was no Nobel Peace Prize in 1948, the year that Gandhi was assassinated. And the Nobel Committee doesn't comment on these things, so it's on speculation. But the speculation is that if Gandhi had not been assassinated, he would have won the award that year.
Okay.
Yeah.
Yeah.
They
I
can't
mean,
give it, they cannot give Nobel Prizes posthumously.
oh, they can't. Okay.
Right. And
I
it's got,
didn't, I,
and so they left it blank in 1948. And again, the committee never answers questions like this definitively, but the speculation is that if Gandhi had not been assassinated, he would have won the Nobel Peace Prize in 48.
gotcha. I know one thing that I learned at the museum was that they will not divulge the nominees for a particular prize until 50 years after a prize is awarded. And they do that so that there, again, this lobbying can't take place to try to, get so-and-so that was on the list but didn't get one, to try to get them, try to have a lobbying effort to get those folks a prize of their own. So yeah, but I did not know that, James. And again, if I'd have gone to the Peace Center in Oslo, I probably would have learned that. But no, I said I'll go find out about this in Stockholm, and I missed the boat. But anyway, thank you for that. Appreciate that. Anybody else? All right. Well, good. Well, I'm glad everybody was able to attend tonight. Um, and with that, I'll wish you a good evening. And again, thanks for coming tonight. I really appreciate it. Y'all have a good evening.